Welcome back to another episode of Dave Does Math from Home. We are going straight into part 2 of our Systems of Linear Equations videos. Here we have a system of linear equations. 4x minus 3y is negative 2, x plus 7y is 15. I think this is a really good example of a problem that would be pretty annoying to try to do with elimination. Eliminating the y's would be, it's possible. You'd have to multiply the top equation by 7 and the bottom equation by 3. That sounds like more work than is necessary. Eliminating the x's would be a little easier. We could just multiply the bottom one by negative 4, which is very possible, but I would prefer to not have to deal with 60s if I can avoid it. The real reason I think that this is a good candidate for not doing elimination is because I think substitution is very easy. Anytime you have a variable without a coefficient, that means that all you have to do to isolate it is subtract the other piece. And now it's ready for substitution immediately. So anytime you have something with no coefficient here, substitution is probably the way to go. And we can plug this thing into this x. I'm going to get that 60 anyway. That's all right. 4 times 15 minus 7y minus 3y equals negative 2. This is my substitution equation that I can now solve for y's. So this is going to be 60 minus 28y minus 3y equals negative 2. So now I'm subtracting 60 from both sides and combining these like terms into negative 31y equals negative 62. So y is going to be a nice easy 2. And again, you have to be very careful to make sure that you don't get your one answer and put a box in it and say you're done. You need to go back and check things. I can plug this into, I'll just plug it into this one. That seems easy. X equals 15 minus 7 times 2. That's 15 minus 14. So according to that, x is 1. And then we're going to double check it in the unused equation. 4 times 1 is 4, minus 3 times 2 is 6, does equal negative 2. That is a big check mark and a happy face because that works. So this is a good example of systems of linear equations that you want to solve with substitution. I'm going to erase this one real quick and put another one on the board that is much more annoying to solve with substitution, so we should use elimination instead. The one I want to solve with elimination is 4x plus 3y equals negative 13, and then 3x minus 5y equals 41. If you try to do this one with substitution, any decision you make is going to involve a lot of fractions. So if you try to isolate this one, then you'll have 5/3 and 41/3. If you try to isolate this, you'll have 3/4 and 13/4. No matter what you do, since all of these have coefficients, you're going to get fractions involved. So I think this is a great candidate for solving it by elimination. And it kind of doesn't matter which one we eliminate. I'm going to eliminate y because I already have the positive negative thing going on. One of the most common mistakes students make when eliminating things is they mix up positives and negatives. Or like if someone was going to try and eliminate these guys, I've seen this happen a lot. Students might try to eliminate the x's by multiplying the top one by 3 and the bottom one by 4, and then subtracting the two equations instead of adding them. You can do that if you're very, very, very careful, but I would advise against it. I see students mess that up all the time, where they're trying to subtract one equation from another and they just drop a negative sign or forget that they're subtracting halfway through and start adding things. It gets messy. I would always advise, if you're going to eliminate on x's, multiply this by 3 and multiply this by negative 4. just get all the negative signs out of the way in the multiplication step and then add. That is my strong recommendation for those. But I'm going to eliminate on the, no, I just said that, so I'm going to do that actually. Let's eliminate on the x's. I want to multiply this by -4. -4 times this whole thing, and I want to multiply this by 3 times this whole thing. Here I'm using x as times. I should use a dot so it doesn't get mixed up with the x's. There we go. So this top equation is going to become 12x, 9y, and -39. The bottom equation is going to become -12x. There's that elimination piece going on, the 12, the -12. -4 and -5 is going to give me plus 20y. -4 and 41 is going to give me -161. -164. Huh, this is not very pretty. That's all right, we can still do this. The x's, when I add these things together, the x's are gone. This is 29y equals -203. And I'm guessing that -203 divided by 29 is not a horrifying number. It kind of looks like it should be horrifying, but that's probably like 7, because this is about 30. Yeah, I think this is 7. So 7 times 29 is going to be 140 and 63. Yeah, okay. So y is -7. That wasn't so bad. And then I plug that back into one of these original equations. So let's say 4x plus 3 times -7 equals -13. This is -21. So if I'm adding 21 to both sides, this will become 8. 4x equals 8. So x is 2. And then we plug both of those into this other equation to check it. Does 3 times 2 is 6. -5 times -7 is positive 35, and that does in fact equal 41. So we are checked, we are happy. Okay, so this is an example of a problem that we really want to use elimination for. The last one was a problem that we really want to use substitution for. There's only a couple more examples that I want to talk about. One of the examples that I want to talk about is going to be something like 3x plus 4y equals 18. And let's do 6x plus 8y equals 21. So again, this seems like a pretty good candidate for elimination because all of these things have coefficients on them that would create fractions if I tried to isolate them. So I'm going to do elimination. The 3 and the 6 looks really tempting, so I'm going to hit this top guy by -2. And the bottom one I'm just going to leave alone. So on top, I'm going to get -6x minus 8y equals -36. And on the bottom, I still have 6x plus 8y equals 21. So I'll add these guys together and I will get 0 plus 0 equals -15. Hopefully we're all paying close enough attention to realize that 0 does not equal negative 15 and that this isn't true and we have a problem, these two linear equations are incompatible. There is no solution. I want to talk very briefly about this no solution business. The section we're going to do next, here's a little preview of what's coming next. The section we're going to do next is about linear functions. So we're going to start putting things like y equals mx plus b onto coordinate axes where m is your slope and b is your intercept. These are linear functions. They have their y equals their mx's and their b's. You could solve this one by saying y equals negative 3/4 x plus 18/4. If you move the 3x over here and then divide everything by 4, this is the y equals mx plus b version of this same function, but they are the same function. When you're solving a system of linear equations like this, and both of these can be thought of as linear functions, you're sort of looking for the point where these two lines intersect. That is the x and y value of their intersection. That's the solution to the system of linear equations, the point where they intersect. When you have two linear equations that don't have a solution, that means they don't intersect, which means they're parallel. So, as lines, these two guys are parallel, they never intersect. There's no point that satisfies both equations, there's no solution. There's just one more example that I need to talk about. And for this, let's do x minus 3y equals 7. We'll do negative 4x plus 12y equals negative 28. For this one, I'm going to do substitution by isolating this x. So this thing is going to become x equals 7 plus 3y. I can plug this into here. So negative 4 times 7 plus 3y plus 12y equals negative 28. This is my linear equation in just y that I can solve. So this will be negative 28 minus 12y plus 12y equals negative 28. Combining like terms mixes the y's, and we have negative 28 equals negative 28, which is always true. It doesn't matter what x is. There's always a y value that solves both of these equations for any given x value. So this is a little bit more complicated than when we were just doing regular linear equations and we got this situation, we said all real numbers work. Any real number for x solves the equation and we're all set. This is slightly more complicated because we're not just talking about any number on the number line for x. The solutions to these things are points on a coordinate grid. And we can't say any combination of points solves this. Any combination of points that's on this line is also on this line because these are secretly the same line. That's what it means when you get a statement that's just always true. You cancel all of your variables and you just have a true statement. That means that these are secretly the same line. It's not that they're parallel and they're never intersecting. It's that they are on top of each other and they are always intersecting. So there's infinitely many points that solve both of these, but they still have to be on these lines. So You can say there's infinitely many solutions, but you have to say that the solutions, you're basically saying x equals 7 plus 3y is the solution set, essentially, which feels like sort of a cop-out. Like, this is what we were given as our problem, and it's also our solution, because our second equation didn't actually help anything. It's just the same line. So on reflection, everything I just said feels rambly and awkward, but I'm not sure how to say it better. So I'm just going to hope that that was clear enough, and I'll suggest that if it was not clear and you are left with lots of questions, you should come find me in the ASC and I will explain more clearly, I hope. But that's it for this section. We have systems of linear equations, two solution methods. We can eliminate, we can substitute. Both are fine. Some work better than others for certain problems. Most of the time, you're going to get a solution set that's an x value and a y value. That's the point where they intersect. Sometimes you get no solution if your two lines are parallel. Sometimes you get infinitely many solutions if your two lines are the same line. And that's it.